Welcome to the lesson on the overview of control systems. Upon completion of this lesson, learners will be able to define a control system and explain its various parts. Learners will also be able to describe a robotic controller system with sensors, algorithms, and actuators, and explain the general features of a computer program, including its various levels. Let us start by defining a control system. A control system is a framework or mechanism designed to manage, regulate, and control the behavior of a device, machine, or process to achieve a desired outcome. It works by monitoring the current state of the system, comparing it to a desired state, known as a set point, and making adjustments as needed to minimize any differences or errors. Key components of a robot control system include set point, sensors, controller, actuators, and feedback loop. The set point represents the desired robot position or state. The controller measures the current state against the set point and drives actuators and motors to reach the target position. External disturbances in the environment may affect robot motion, requiring controller compensation. The physical process involves motion dynamics and incremental movements. Sensors provide real-time feedback about position and environment, enabling precise controller adjustments. When a design point is entered, the controller uses sensors to compare it with the current position. The controller activates actuators to eliminate any detected offset between desired and actual positions. The physical system experiences disturbances and processes that affect overall system behavior. A robot control system uses mechanical and electrical devices to regulate robot behavior through a continuous feedback loop. The system centers on a set point, the desired robot position or joint configuration. The controller compares real-time sensor data about the robot's current state with this set point, then directs actuators and motors to move accordingly. The system actively compensates for external disturbances like physical obstacles while managing motion dynamics. Sensors provide constant position and environment feedback, enabling precise control. Let's take a look at the big picture of the robot controller. The robot controller itself is essentially a small, programmable computer. It's not necessarily the same size or as capable as a regular desktop or laptop computer. Sometimes it may be more powerful, but often it's less powerful and designed for a specific set of tasks. These tasks are carried out very efficiently and are based on programs that you design or write in software, which are then loaded onto the controller board. For example, the program might be as simple as instructing the robot to move from point A to point B and back to point A again. Alternatively, you might program a conditional sequence, such as go to point A, then to point B, and if a specific condition is met, proceed to point C, or another set of predefined actions. As we discussed previously, the controller receives all this information, processes it, and compares what we, as programmers and operators, want the robot to do and how it interacts with its environment. This is achieved through the use of sensors, algorithms, and actual instructions that are translated into signals for actuators. In the case of industrial robots, there's often an added layer of complexity. Instead of being limited to a standalone programmable computer, they frequently have connections to a server or an interface. This enables them to connect to a network, allowing us to program or operate them remotely. Let's take a look at this video, which provides an overview of the various components of a robot control system. We will look at some of the ways these controllers can be applied in different scenarios.
Robots. We see them everywhere. They assist humans in performing repetitive and dangerous tasks. They can be as small as a cent or as big as a building. They can explore inner depths of the earth or the outer reaches of the space. Robots are currently being used in the fields like manufacturing industries, aerospace, healthcare, military, and the list is endless. In manufacturing industry, tasks such as welding, painting, assembly, and testing are carried out by robots with high precision. But it all started with a giant robot arm. In 1961, the first industrial robot, Unimate, was used in the assembly line at General Motors plant. By simply pushing buttons, you could move Unimate and record the positions for it to repeat them. A magnetic drum is used to store the instructions, which will be implemented in a step-by-step process. Since then, we have come a long way. But how is this possible? A robot observes, decides, and acts. Sensors observe the environment and provide feedback to a controller. Modern robots are equipped with a variety of sensors such as cameras, gyroscopes, IR sensors, and LiDAR. The controller is the brain of the robot that takes the information perceived by the sensors and makes decisions. The signals generated by the controller are sent to the robot's actuators to perform actions. As the robot moves, the sensors perceive new information and provide that information to the controller, and this completes a feedback loop. A dual to the classic control problem is known as estimation. Often, we do not use raw sensor data. We run algorithms on sensor data to estimate the quantities we want to measure. For instance, in an application called Simultaneous Localization and Mapping, or SLAM, we estimate the 3D geometry of the feature points of the environment and the robot's location simultaneously using a 2D camera. And that's how the robot can control its position even though it doesn't have a GPS. The motion of the robot must be controlled so as to perform a certain task. This is usually done by programming. Programming industrial robots can be divided into three basic methods: teach mode programming, lead through programming, learning from demonstrations. In teach mode programming, a person can use the switches on a teaching pendant to guide the robot through a sequence of events. The positions are stored for the robot to repeat the actions with the help of a controller. This method is very useful in teaching simple movements. However, this may not be preferred where robots are frequently reprogrammed. The next method is lead through programming. In this method, a person will lead the robot manually through the desired positions. The robot will store these positions and repeat the movements using a motor controller. The third method of programming is learning from demonstrations. In this method, the robot collects a set of demonstrations of the user performing a certain task. Then a mathematical function is generated to encode this task. Using this mathematical function, reference commands are generated for the robot to follow. The robot controller knows its current state from the sensors which it uses to generate a mismatch or an error between the reference commands. This error is used by the robot controller to correct its position and orientation. Since the robot was taught to perform a task by encoding the task in a mathematical function, this function can be used to reproduce reference commands in different situations, such as avoiding obstacles.
Now that we've looked at the controller and the robotic system as a whole, let's briefly discuss the computer and the programming involved in controlling the robot and moving it as we desire. As an overview, computers are binary digital systems. This means that everything within them operates as either on or off, represented by zeros or ones, forming a discrete binary value system. It's important to understand that, as operators and programmers, we need an interface to translate our written language, desired actions, and intended outcomes into something the computer can process. This process converts our instructions into the binary digital system the computer uses. As programmers, operators, and technicians working with robots, we must have a foundational understanding of how to create software code and develop instruction sets for robots and controllers to execute effectively. Now, let's examine the architecture of computers that execute our programs. We will begin at the lower levels and build our way up to higher level languages, which are more familiar to programmers, operators, and technicians. The levels include hardware, machine language, assembly language, and high-level language. We start at the bottom level, which is the hardware. This includes components like transistors, actuators, and devices that handle electrical signals, store information, and operate switches. These components execute instructions via the hardware's instruction set, driving the physical aspects of computation. The next level up is machine language, the binary digital system that forms the basis of software instructions. Machine language consists of zeros and ones, or ons and offs, that directly control the hardware. For instance, these binary instructions might toggle pins, perform arithmetic operations using digital logic gates, or trigger specific hardware actions. Machine language is highly specific and directly translates into hardware behavior. One level above machine language is assembly language, where we start to see instructions that are more understandable for operators and programmers. These instructions include adding and subtracting numbers, comparing values, fetching data from memory, and executing commands. Assembly language is something we could program directly, but modern tools make this unnecessary by translating higher-level code into assembly and then into machine language. At the highest level, we encounter high-level programming languages. These include classic languages like Fortran and C, and more modern languages like C++ and C#, which build on the foundational languages. Visual and object-oriented programming languages add layers of complexity to make programming more intuitive and expressive. This complexity allows us to write sophisticated algorithms and programs easier for humans to understand while still being translatable into machine-readable instructions. By the time we reach high-level languages, the code is written in an intuitive and highly readable format. These languages enable us to communicate our ideas effectively, using well-established syntax and structures that abstract away the complexities of the underlying machine operations. Now, we will reverse the process to understand how we go from something we comprehend as programmers to what the machine, robot, and controller are actually executing. The software programs we write are typically created using a high-level programming language, as mentioned earlier. These languages are designed to resemble human-readable text, allowing us to write commands in a form that is easy to understand. For instance, we might write a simple condition such as, if this condition is met, then execute this action, in plain text format. Once we have written the high-level language program, a compiler is used to convert it into a lower-level form, such as assembly language. Assembly language is less human-readable than high-level languages, but it more closely represents the actual actions carried out by the computer. After this step, the assembler takes the assembly language code and translates it into machine language. Machine language consists of binary instructions, represented as ones and zeros, which the computer hardware can directly execute. This process involves converting the numerical and logical commands from the high-level program into binary format so the computer can process them. Finally, this machine language is executed on the hardware by the central processing unit, abbreviated as CPU. The CPU is the central piece of hardware responsible for managing tasks, such as accessing and storing data in memory, controlling the arithmetic logic unit, abbreviated as ALU, to perform calculations, and managing the flow of communication across the robot and computer system. This entire process enables the robot to carry out the intended actions as programmed. In summary, control systems are responsible for regulating dynamic systems. They may use open-loop control, where there is no feedback or sensors in the system, or closed-loop control, where sensory feedback provides information about displacements from the set point or disturbances in the environment. Robot controllers are typically compact and specialized computers designed to execute focused instructions based on what the user or programmer wants the robot to do. When programming robots, high-level language commands, like moving to XYZ coordinates, are compiled into assembly language, converted to machine language, and executed by the hardware. Thank you.